Wasn't there something we were going to
You guys, you want gum here?
I think you might have to be a little bit louder.
But I don't.
Okay. Never mind then. So,
Hey guys, it's Allie. The class wants you guys to bring back candy for us, preferably gummy bears. Hope you're having fun. Sorry you have to do physics in Germany. Bye, I love you. Luke Corella says hi. And Olivia Sampson. Everybody says hi.
except for Aiden. All right, so we're at the, you guys were, you had done your predictions, right? And let me just look, you're still working alone. You have, how many people are ready? How many people have it all the way down to the stop sign? Or are we still in the middle of that? Yeah, I'm just trying to gauge where you are because my thing was at the top of page 2, which says to me you guys haven't quite finished your predictions yet. Right? So let's take a couple more minutes without talking to your neighbor. Finish your predictions to the stop sign, and then we'll have you talk to your neighbor. I think we did go over this stuff you put in Socrates, though, right, Alec? Alec, right? Okay. So finish off your prediction, then we'll come back to you. Remember that while talking to your neighbor, your task is to convince them that your answers are correct, and you two should agree on your answers. All right. So give them a talk, see what they, see where you can come to agreement. Any group willing to share their prediction up front for us. Thank you. And if Luke makes fun of you, we will discipline him. Since he said he was going to make fun of you. Oh, sorry, I misheard you. I misheard.
Gummy bears.
It is recording now.
Yeah, it's still recording.
Well, not still. I just turned it back up.
It's Justin with the pencil. The pen. The marker. Yeah.
Yes.
It's like circle. Let's like circle all. Like with like. And then. Okay. And just draw with the thin marker. Now you're gonna take off the ink. Alright, you can get the pen. You're not ready?
Thank you, Jim. So is there agreement, disagreement, questions for the group to share? She asked if you were saying that they're all the same. It looks like you are. Yeah. And you're saying there's only current when the switch is open. When it's closed, there's no current. And then when it's reopened, there's current again. Okay? What do you guys think? Do you agree? Disagree? Well, I'm not saying whether it's right or wrong. It's obviously right because it's not blank. But do you agree with it? Do you like it? You said it's a little funky, so I don't know. Do you like funky? Do you not like funky? We'll go on to Luke, though. Why do you think about that? You agree? You like? Why do you agree? Okay. Okay. Any other thoughts? Excellent. Thank you for sharing, gentlemen. Appreciate it. So what you want to do is now turn over the page. And I need to move that over a second. And so you should be now where it says Part A results. And we'll use our simulation to get our results. I would suggest, because the graph will stay here after I repause the simulation, I would suggest watching the light bulbs while the switch is going. Remember, I'll have it open for the first 4 seconds, closed from 4 to 8, and then reopen from 8 to 12, and then I'll pause the simulation. All right? And our colors are red for the battery, blue for the left-hand bulb, and green for the right-hand bulb. So, all right, Alec, you ready? Okay. Here we go. So it's open, and then it's closed, and then it's open again. Now, what color is that line? So what do you think that tells you? That it's green, blue, and red. They're all the same. It's drawing 3 lines right on top of each other. What did you notice about the state of the bulbs? How were they when the switch was open? Okay, both of them? Yes. What about when the switch was closed? Both of them were on. So the correct pattern, because they were off, then on, and then off, is pattern F. So the correct part A was FF. So here you'd want to have FF. So which of the 4 models best predicted the current? A, B, C, or D? Remember, you can flip back a page to look how they're written. Guys, you really, I'll warn you, this stuff builds on itself. So if you're like, hey, I'm sitting in the back of the room, so I don't need to listen or pay attention, I can just screw off. In about 3 or 4 days, you're going to be like, when did we ever learn that? And guess what it was? Because it steps up to the top. It's not ignore and then suddenly you can leap up there. So really encourage you, no matter where you're sitting, to pay attention as we go through these steps. All right? So which model? Model D would be the best one. Where the current flows in the direction shown, the current will be the same in both the bulbs and the battery. And we see that by the lines being right on top of each other. Is that what we see? That's shown by the lines being right on top of each other, so much that we only have 1 line on our graph, but it's multicolored. What's another piece of information this graph gives us about the current? Well, I don't know. I don't know if I put it that way. What's showing you that it's not constant? Oh, so what's the difference between this part and this part, the 0 to 4 and the 4 to 8? What was different from 0 to 4 seconds and the 4 to 8 seconds? The switch was closed for which part? For 4 to 8. And so when the switch is closed is the only time that we have current. So we need a complete circuit or a complete path for the current to exist. If there's a break in the path during 0 to 4 or 4 to 8 when the switch was open, there's no current. So to have current, you have to have a complete path, a complete circuit. And that's why we use the term open and closed with switches, say whether or not they make a complete circuit, a closed circuit versus an open circuit. So hopefully you notice that. Now we need to come up with a general rule for this part. What type? Nope. That's true of any circuit. That's one of the things hopefully you now realize if you didn't realize it before. Right, that's another way to think about it. You don't have that complete path. You need that completeness. What we want to come up with is something about. Anyone remember what type of circuit is this? Series, right? This was a series circuit because the two bulbs are in a series with each other. They're in a line. The type of circuit's always described by the elements. So this is a series circuit, and we just looked at current. So we want to come up with a rule that describes this current during the 4 to 8 section when it was a complete circuit. How is that current? What can we say about that current in a series circuit? What do you think? How does the current in the battery and the two bulbs compare to each other? They're all the same. So somehow you want to put together a sentence that says, like in a series circuit, the current is the same, or the current is constant, or there's only one current. However it triggers in your mind. But you want to get the ideas of it's a series circuit, and everywhere has the same current. So put that you would do on page 4 at the bottom, where it says, what is the general rule for this part? So something in there. Let's move on to part B. And we have a slightly different circuit arrangement. All right, so we have a circuit made up of the exact same elements as we had before. Switch, battery, and 2 identical bulbs. But this time, the bulbs are not arranged in series. What do you think you call that arrangement? Parallel. I think about it, if series is living on the same street as somebody, this is living 1 block over from them. All right, so you have so this would be a very simplistic, but a parallel circuit because the 2 bulbs are in parallel. Again, we're looking at current. We'll look at current through the battery, current through the top bulb, and current through the bottom bulb. So you're asked to predict the state of the bulbs when the switch goes open, close, then open again. Basically the same predictions that you were doing last time, all the way down to the stop sign. And I will turn on I'll turn on Socrative so you can enter yours in there. Oops. I forgot to turn that. Oh, that's the part I want. Do we have a group that'd be willing to share their? Thank you, Richard. That'd be great. Whatever works for you. So the blue one is the battery. Yeah. Okay. All right. What do you guys think? Do you agree, disagree? Questions for the partnership? Do you agree? Now, which model would that go along with? Model D. Yeah, it would fit with Model D. So, and that's one good thing always to check, right? Because you just pick the model. You want to draw a graph that would reflect what you think the model's going to be. So, how many people who picked D drew a graph similar to this? Oh, good. Bunch of you. Good. Excellent. So at least it agrees with the model that we picked. Maybe it's right, maybe it's wrong, but we have some agreement. All right, so now let's move on to page 7 here, where we're going to get to the results. All right. So here we go. Let's see what we get for results here. So we'll go open, 0, that's pretty good. Close, and then open again. Yay. So we saw again that the current only exists when there's a closed circuit. Right. So do you think that's why I make sure we use those terms? Give you a minute to copy that down. So hopefully maybe there's something in number 4 that you realize now that you didn't before. But what can we come up with as a general rule for current in a parallel circuit? Now that's the situation we see here. Do we think that'd be true if we had 3 bulbs? Or 4 or 5? Okay. Yeah, because we see that. It looks even, right? If we add up these, they add up to the red. But do you think that might be because we have 2 bulbs and they're identical bulbs? It might be. So we want to keep as general as we can. So how can we put those ideas together but make it more general in case we have a big bulb and a little bulb and 3 bulbs or 7 bulbs? I'd even go more general than proportion. Drops evenly. Because evenly, maybe it's because these two are distributed. Yeah, that's a good word. I think of it as it's distributed or it's split between the elements. So what's happening here is the current is coming. Remember, current is the movement of the charges, right? You learn that in the first part of that, the interactive that you guys did. It had the pinwheel, had the blue electrons moving by it, spinning it. That's the current. So in a parallel circuit, the current splits, divides, distributes between, these are known as branches. So distributes, splits between the branches or the elements. So the current comes up here, and then it hits this breakpoint, which actually is called a junction, and it splits, it divides up, because some has to go each place. So we're on to part C, and we're looking at our series circuit again. Made up the exact same circuit we looked at before, but this time, rather than looking at the current, we're going to look at the voltage. So we're going to look at the voltage across the battery, the voltage across the left-hand bulb and the right-hand bulb. Now, voltage, if you think back to the stuff you did a little bit earlier, voltage is the amount of energy each charge has. So it's energy per charge. What type of charges are we talking about? Electron. So it's actually how much energy each electron has. And that's why whenever we talk about voltage, we have to talk about voltage difference or potential difference. So we don't just say, oh, I'm going to measure it right here. As much as we say, hey, what's the difference between, say, this side of the battery, the positive side of the battery, and the negative side of the battery? How much energy do the electrons that are on the positive side have compared to the ones that are on the negative side? On the bulbs, how much energy does the electrons that are coming into the bulb have compared to the ones that are coming out of the bulb? So when you're looking at voltage, you're always comparing how does it change across something from one side of it to the other. And that's why you'll commonly hear, what's the voltage across the battery? What's the voltage across the left-hand bulb? Across the right-hand bulb? So it's not a static, hey, what is it at this point? But what is it from one side of this element to the other? All what's gonna be measured in this with the switch open, closed, and then open again. You're gonna measure the voltage across the battery and across each of the bulbs. Go ahead and do your prediction. Notice it's only that one page this time. It's the graph and some other questions. Only one will work at a time. Thank you. Appreciate it. Folks, what's your opinion? Do you agree, disagree? You disagree? Okay. The whole thing, or Allie, can you join this conversation, or at least not distract? So it's like, it's high here and then it drops down. So kind of the inverse of this, the opposite. Okay. All right. They're in series for this one. Okay. Oh, yeah, no, they aren't on for this. We didn't remember when there was no current, there was no light. Other agreements or disagreements? Sam, what do you think? So you like this, except you would move the red up to a constant line. Okay. Interesting. Let's see. Let's see what happens. So turn over to the next page. Page 8. And let's see what happens. So here we go. Let's see. Unpause, open. Oh. Closed. Open. And paused again. Interesting. Close. Close to Sam's prediction. What produces the energy out of a battery? Yeah, what produces that voltage? Chemicals. The chemicals in there. Think back to chemistry, electrochemical reactions. So the chemicals that are inside this battery are what are producing the energy the electrons have. So no matter what happens with the switch, the electrons on one side have more energy than the electrons on the other because of that chemical reaction. The other way to think about it is, as the electrons move through the battery from one side to the other, no matter what the switch is doing, they're gaining energy. All right. So this is the battery voltage. The difference in energy from one side to the other is constant, no matter what's happening with the switch. What about the bulbs, though? Is the voltage across the bulbs constant, no matter what the switch is doing? No. How does this graph compare to the graph of current from part A? That would be page 3 you want to look at. Compare this graph to page 3 in your notes. How does it look? Look, it's a similar shape, right? How much current was there from 0 to 4? None through the bulbs. How much voltage through the bulbs? None. And then was there current from 4 to 8 through the bulbs? Yeah. And then back to none. So for the light bulbs to have voltage, there has to be a current through them. These are hopefully things that maybe you didn't know that you're writing down in number 4. You know, that the voltage across the battery is constant because it's provided for by the chemical reactions in the battery. That the voltage across the bulbs only exists when there's current. And what do we notice about the voltage across the bulbs compared to the voltage across the battery? It looks like it's half. So do you think if we added these two up, they'd add up to the red? Yeah. We had current that was similar to that. And what did we make up for a general rule in section B when we had current that looked like this? Distributed splits. So what do you think we can say about voltage in a series circuit now? Distributed or splits among the elements, or however you want to say that. But the idea is that each one takes some of the voltage. Do you think the half is just coincidence? Or is it the fact that we have two identical bulbs? So if we had three identical bulbs, how do you think it would split up? Maybe into thirds. And if we had three that were all different, they may split up differently. But the rule would still hold that they would add up. They'd combine to be the total voltage, or the voltage of the battery. And part of that idea is that the electrons that leave the battery as they make it around the circuit, they've got to give up energy to move through the light bulbs. How do we know that energy comes out of the lights? Alec, how do we know that energy comes out of these light bulbs? What do you mean by turn on? They illuminate, they give off light, and that's energy, right? So the electrons, as they move through here, have to use up energy to get through there. So if you think about a single electron, it gains energy in the battery, and then it's going to drop some of it across one bulb, some across the other, before it gets back to the battery. We'll look at that idea a little bit more in depth. But that's what this graph is saying to us. What type of circuit? Parallel. But this time, remember, we're looking at voltage, not current. So you're looking at the voltage across the battery, voltage across the top bulb, voltage across the bottom bulb.